All right, in this video, we're going to be discussing circular motion. So it's going to be important for me to define a few terms before we start. All right, the first term that we're going to discuss is called tangential speed. This is how you spell tangential speed. It's abbreviated with a V sub t. And let's take a look at what it looks like here. I brought in two ladybugs for us to look at. And I'm going to put them on a turntable, like a DJ record player type turntable. And we're going to let them turn. The tangential velocity is the speed at which this bug is moving in a straight line. So if I pause the video, right, we see as the bug goes around the circle, at this point in time, her speed tangent to the circle is in this direction. In other words, if we were to draw the bug here, tangent to the circle is an imaginary line that intersects the circle there, right? So we know from math that this is the tangent to the circle. So at this point, her tangential speed is in this direction, and it's of that magnitude, the length of the arrow. We know that velocity is a vector, or is a vector, which means it not only has length, but it also has direction. Of course, as the ladybug turns, right, her tangential speed changes direction. But notice its magnitude never changes. Now, what I'm going to do now is I'm going to move the ladybug to the outside of the circle. And we see now, if I were to pause this video, we see now as she comes around the turn here, again, her tangential speed is here tangent to the circle, but now it's a much greater speed. Why was it a smaller velocity or speed here than it was here? Well, her tangential speed is greater here on the outside of the circle because, you ready for it? Here it comes. She's going to do one complete circle in the same amount of time no matter where she is on the record player, right? This goes around once in a second. So if she's here, she goes around once in a second. And if she's here, she goes around once in a second. However, if she's here, she has to cover a much greater distance than if she were here. So therefore, her velocity must be much greater. Her tangential velocity must be much greater. So this has an interesting implication. Here we have a video of the rotating Earth, right? So here's the Earth as it spins. And if you think of the Earth, it's a circle, but it's a three-dimensional circle, so it's a sphere. But the Earth is the fattest, or the circle is the biggest at the equator, and then the circle gets smaller and smaller and smaller till you get to the North Pole. Well, if we think of our ladybug example, remember the closer you were to the middle, the less tangential velocity the ladybug had. So what's interesting about the spinning Earth is the closer you are to the equator, the faster the higher, the greater your tangential velocity. And here's a neat graph that shows the tangential velocity or tangential speed at Earth's surface due to rotational motion. And we see here is in miles per hour. So if you're at either the south or the North Pole, which is 90 degrees there or there, your tangential speed is 0. You're standing right here in the middle of the circle, so you're not going to move. As you move to higher and higher, or lower and lower latitudes, right, as you come down, the circle the Earth makes gets a little bit bigger, so your speed increases. And you can see Chicago is in the northern hemisphere at about 41 degrees, so we'll say maybe we're out there. So our speed as we rotate is somewhere around 700 miles per hour. So you are moving 700 miles an hour. So if you get pulled over or you see a cop and he says, "How fast? Do you know how fast you were going?" You bite your tongue and don't be a smart aleck and tell him, "Oh, we're actually going 700 miles an hour." But you are going 700 miles an hour. And what's cool is at the equator, you see that they're going almost 1.5 times as fast as us. So people that live in Singapore or in parts of Africa or so people in the South of America even are going faster than us, right? This is also why they launched the space shuttle from Florida, right? Here's Florida, right, which is at about maybe say 30 degrees. So we see that they have a higher tangential velocity, 900 miles per hour versus say 700 miles per hour in Chicago. So that extra speed is a little extra energy that the space shuttle, space capsule can get as it enters the atmosphere. So that's kind of stealing from Earth there. That's kind of cool. Now, as we look at the ladybug again, we see a second vector, and it's labeled A. And this is going to be our second term. And the term is pronounced centripetal acceleration. So centripetal acceleration is the acceleration due to a change in direction of the velocity of an object going around the circle. If you remember, velocity is a vector, right? So it has both magnitude and direction. Well, the magnitude of this doesn't change as the ladybug goes around the circle, right? We see that the magnitude stays the same, but we're changing the direction constantly, and so we need an acceleration, and that's called the centripetal acceleration. A couple things about the centripetal acceleration. Notice that it's always at a 90-degree angle to the centripetal velocity, or the tangential velocity, the tangential velocity. We see they're always at a 90-degree angle to each other, which means the centripetal acceleration always points to the center of the circle. So that's very important for us mathematically as when we get to the math. So I'm going to write that here. Put that right here. So the centripetal acceleration always points to the center of rotation. All right, so let's look at why the centripetal acceleration is towards the center of the circle. Here's a simplified picture of a circular object going in circular motion. Here we have the initial velocity of the object, and here we have the velocity at some time t afterwards, right? So again, the direction has changed. The magnitude of the velocity has stayed the same. But we will see that if you remember back to season 2, we know that acceleration is equal to a change in velocity over time, which is Vf minus Vi over t. Well, what we have here is we have Vf and we have Vi, or V initial, original. That's for the O. We need to do this to them to get acceleration. So what we're going to do is I've got to take Vi and I've got to make it a negative Vi. So how do I make a vector negative? Well, I turn it around the other direction. So I actually make a vector that goes this way, right? And what we see now when I add that vector here, going that way, we see that we get an acceleration, right? So now I'm going to take vector 1 plus vector 2. So I'm going to find the hypotenuse, which is going to be my acceleration, and that's towards the center of the circle. Okay, and it wouldn't matter where these two velocities were taken from. If we did it like down here and here, we would still get a resultant towards the center of the circle. So that's getting it from Vf minus Vi. Vf minus Vi will always give me an acceleration towards the center of the circle. Okay, there is an equation. The geometric proof is a little tricky and probably a little bit above a 3-level physics class. If you're interested, let me know. I'd love to go over it with you on the board. It's kind of fun. But this is the equation that you should put on your equation sheet that'll help us do math relating to centripetal acceleration. And we'll do a practice problem right now so you can see how this gets a kind of a test run. So this problem is taken from page 235 of your textbook. But we'll see here what we have. It says a test car moves at a constant speed around a circular track. So is this the tangential speed? If you said yes, you're right, because he or she's going around the circular track. And it says if the car is 48.2 meters from the track's center and has a centripetal acceleration of 8.05 meters per second squared, what is the car's tangential speed? Well, this r in the equation for centripetal acceleration is the radius of the path the car's in. So we can imagine here we have a car going around the track, and we know the radius of the track. This distance is 48.2 meters, and our car is going around the track, right, tangential to the circle. So it says, what is the car's tangential speed? So we're trying to find this car's tangential speed. So let's figure out what are our knowns here. So our knowns are the radius of the circle. We know the radius of the circle is 48.2 meters. And we also know the Centripetal acceleration is 8.05. And notice the units here. These are the same as the units for what we would call linear acceleration, or this acceleration we've used so far this year. So I know my AC is 8.05 meters per second squared, and I want to find my tangential velocity, right? So now I'm just going to plug in for AC 8.05 and multiply by 48.2, and we're going to plug and chug, and you get a tangential velocity in this case of 19.7 meters per second. This is a really fun unit. I know I say this every time. Lots of cool demos, and it's also the most conceptually can be demanding unit of the year. So hang in there. If you're not getting it right away, bring your questions to class or email me, and I hope that was fun.